This is section 11.4, Introduction to Derivatives. I'm going to talk about the slope of a secant line, slope of a tangent line as it relates to the difference quotient. So let's find the secant line from the point 2,4 to the point 1,1. And so we have this secant line right here. And the way that we get the slope of that secant line is we do y2 minus y1 over x2 minus x1. Now this is the point 2,4. And this is the point 1,1. We're going to take 4 minus 1 over 2 minus 1. That's 3 over 1. So the slope of the secant line is 3. Now we're going to work our way to the slope of the tangent line. Now the problem with the slope of the tangent line is there's only 1 point. So how are we going to find the slope of the tangent line with only 1 point? We need another point so that we can do y2 minus y1 over x2 minus x1. Well, here's what we do. We get closer and closer. Let's say we go to 1.5. What is 1.5 squared? Grab a calculator real quick, clear that. We go 1.5 squared, and that's about 2.25. So 1.5 is 2.25. So on the curve, that's about right. Well, about right there, actually. Yeah. So we could do the slope of that secant line right there. Slope of that secant line. And we're getting closer to the slope of the tangent line. Or what if we did 1.25 squared? 1.25 squared is 1.56. So 1.25 squared is up there, right there, on the curve. And if we did... Can we do a different color for this? Let's do this. And 1.25 squared. And if we did the slope of that secant line, now we're really getting close to the slope of the tangent line. Well, we could take that, we could do that infinitely close, and we could have 2 points that are extremely close together. So we could have the point 1, and we could have 1 plus, let's call it h, where h is extremely tiny. What if h was 0.0000001? So we'd have 1 and 1.0000001. Those 2 points would be extremely close together. And then we'd have this number. We'd have that number squared as the y value. Then we could do y2 minus y1 over x2 minus x1. So wouldn't that be, this would be f of 1 plus h, whatever, but the function would be squared, right? So we could have whatever function we have, f of 1 plus a little tiny bit, just slightly more, minus, this would be f of 1, and 1 squared happens to be 1. So this would be f of 1 over, then we could have 1 plus h, and then minus 1. But this would happen every time. So it'd be f of 1 plus h, that'd be y2, minus y1 over just h. And h would be extremely small. And if h was extremely small, then that slope of the secant line would be very close to the slope of the tangent line. Now I made a spreadsheet to kind of demonstrate this. We have, what is the slope of the line tangent to y equals x squared, x equals 1? So 1 squared is 1, and then here's something very close to 1. But what if we got even closer and closer and closer? The slope here is 1.9, and as the x values get closer and closer and closer to each other, this slope is approaching a value of 2. It's going to 1.9 as x gets closer and closer to 1. And when you get down here at 0.999, almost 1, the slope is almost 2. And as the difference in the x's gets smaller and smaller and smaller, we get closer and closer and closer to the slope of the tangent line. All right, well, the next slide kind of sums this up. It says slope of the tangent line to a curve at a point. And the point, let's say, is, well, they say a and f of a. So a and f of a is your point of tangency. Now we want another point that's extremely close, where h is very, very small. And then this is going to be f of a plus h. There's the y value. So those are the y values right there. Now we're going to, the slope of the tangent line is the limit as h approaches nothing, as the difference in the x's approach 0. So this is going to get so small, we're going to consider it 0. Now we're going to take it all the way to 0, actually. Well, y2 minus y1 would be f of a plus h minus f of a, and x2 minus x1 would be a plus h minus a. That's x2 minus x1. Now those a's cancel out, and it's just always going to be h. Now let's take an actual example here. Find the slope of the tangent line to the graph of f of x equals x squared plus x at the point 2, 6. All right, we're going to take the limit as h approaches 0 of, well, if the point is 2, 6, then a point very close would be 2 plus h comma f of 2 plus h. But we have a function, so it's 2 plus h, and then 2 plus h squared plus 2 plus h. So now if we take y2 minus y1, we get 2 plus h squared plus 2 plus h. So that's plugging 2 plus h in for the x's. Minus 6, there's f of 2 over h. Now we just have some algebra to do. So limit as h approaches 0 of 4 plus 4h plus h squared plus 2 plus h minus 6 over h. Well, 4 plus 2 is 6. 6 minus 6 is 0. So we have the limit as h approaches 0 of, let's see, that's gone, that's gone, that's gone. 4h plus h is 5h plus h squared over h. Now we can factor an h out on top and cancel it with the h in the denominator, so we end up with 5 plus h. Well, h is approaching 0, so we have 5. The slope of the tangent line of this curve right here to the point 2, 6 is 5. Was there a checkpoint? Nope, there's nothing down there. Find the slope of the tangent line to the graph of x squared minus x at 4, 12. We have the limit as h approaches 0 of f of 4, we'll do this, f of 4 plus h, that's y2, minus f of 4, that's y1, over just h. And it's really x2 minus x1, but it always becomes h. We have the limit as h approaches 0 of, let's go with 4 plus h squared minus 4 plus h. There's y2 minus y1 over h. Limit as h approaches 0 of 16 plus 8h plus h squared minus 4 minus h minus 12 over h. And again, the constants need to cancel, so all those cancel. We have the limit as h approaches 0 of 8h, actually is going to be 7h. 7h plus h squared over h. We can factor an h out on the top, cancel with the one on the bottom. That's 7 plus h, so the slope is 7. Find the slope-intercept equation of the tangent line to the graph of f of x equals square root of x at 4, 6. Find the slope-intercept equation. So y equals mx plus b. Well, we need a point, and we have a point. There's the point of tangency, and we need the slope of that tangent line. We're going to do the limit as h approaches 0 of f of 4 plus h. We'll do this. F of 4 plus h minus f of 4. That's y2 minus y1 over x2 minus x1, which always becomes h. Limit as h approaches 0 of, I need 4 plus h in here. So square root of 4 plus h minus f of 4 is 2 over h. Now we're going to multiply by square root of 4 plus h plus 2, the conjugate. Square root of 4 plus h plus 2. And we have the limit as h approaches 0 of 4 plus h minus 4 over h times square root of 4 plus h plus 2. Well, the 4's are going to cancel, then the h's cancel. We get limit as h approaches 0 of 1 over square root of 4 plus h plus 2. Now when we plug 0 in for h, we get square root of 2, or square root of 4 is 2 plus 2, we get 1/4. So the slope is 1/4. we need y minus 2 is equal to 1/4 times x minus 4. That's the point slope form. So y minus 2 equals 1/4 x minus 1, and y equals 1/4 x plus 1. Checkpoint 2, find the slope-intercept equation of the line, a tangent line to the graph of f of x equals square root of x at 1, 1. We have the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. And that's a limit as h approaches 0 of square root of 1 plus h minus square root of 1, which is 1, over h. And we're going to multiply by the square root of 1 plus h plus 1. And we have square root of 1 plus h plus 1 in the denominator as well. This is equal to the limit as h approaches 0 of 1 plus h minus 1, because you have negative 1 times 1, over h times square root of 1 plus h plus 1. That's limit as h approaches 0 of, well, the 1's are going to cancel. Then once that happens, the h's cancel, and we get 1 over square root of 1 plus h plus 1. And when we plug 0 in for this, we get 1/2. 1/2. So now we have the point 1, 1 with a slope of 1/2. Let's go y minus 1 is equal to 1/2 times x minus 1. That's the point slope form. And we get 1/2 x minus 1/2. So y is equal to 1/2 x. And then when we add 1, negative 1/2 plus 1 is plus 1/2. The derivative of a function, example 1 and 2, we found the slope of a tangent line to the graph of f at a, fa, where a was a specific number. We can also find the slope of the tangent line at x, f of x, where x can represent any number in the domain of f, for which the slope of the tangent line is defined. The resulting function is called the derivative of f at x, which means instead of plugging a specific number in for x, we're just going to leave it as x. Find the derivative of f of x equals x squared plus 3x at x. That is, find what we call f prime of x, or the derivative of x. So f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And that's equal to the limit as h approaches 0 of, we're going to plug x plus h in for the x's, x plus h squared plus 3 times x plus h. And we're going to minus plugging x in for x, which is x squared plus 3x. We're going to be careful because it's a subtraction. So we're going to subtract the whole thing over h. Well, now we're doing the exact same thing, except we're not using values. We're just using the letters, x. Limit as h approaches 0 of x squared plus 2xh plus h squared plus 3x plus 3h minus x squared minus 3x all over h. That's the limit as h approaches 0 of, let's see, the x squareds are gone. Bam, bam. The 3x's are gone. And what we're left with is 2xh plus h squared plus 3h. And that's over h. Now we can factor the h out of the top, cancel with the 1 in the denominator, and we're left with 2x plus h plus 3. And then when we plug 0 in for h, we're left with 2x plus 3. Let's do the same thing for this one. We have the limit as h approaches 0 of x plus h squared minus 5 times x plus h. Then we're going to subtract x squared minus 5x. That's f of x. So we have f of x plus h minus f of x over h. And then we just have a lot of algebra to do. Limit as h approaches 0 of x squared plus 2xh plus h squared minus 5x minus 5h minus x squared plus 5x. Now remember, we're subtracting, so we have to subtract this whole thing. The x squareds are gone, the 5x's are gone, and we have the limit as h approaches 0 of 2xh plus h squared minus 5h all over h. And we can factor out an h on top, cancel with the 1 on the bottom. So 2x plus h minus 5. And when we plug 0 in for h, we get 2x minus 5. Average and instantaneous rates of change. Average rate of change. The average rate of change of f from x equals a to x equals a plus h is given by the difference quotient. So this is really y2 minus y1 over x2 minus x1. Instantaneous rate of change. The instantaneous rate of change of f with respect to x at a is the derivative of f at a. So this is average velocity or average rate of change. This is instantaneous rate of change at a value. So we're going to find the average and instantaneous rate of change. The function f of x equals x to the third describes the volume of a cube, f of x, in cubic inches, whose length, width, and height each measure x inches. If x is changing, A, find the average rate of change of the volume with respect to x as x changes from 5 inches to 5.1 inches and from 5 inches to 5.01 inches. So for letter A, we have 2 points. We have the point 5 and 5 to the third, which is 125. And we have 5.1, and let's see what 5.1 to the third is. 5.1, let's turn the calculator on. 5.1 to the third is 132.651. All right, so the average rate of change is 132.651 minus 125 over 5.1 minus 5. So 132.651 minus 125, and we're going to divide by 5.1 minus 5. So the average rate of change is 76 what was that? 5.1, and that's going to be hx is measured in it's going to be cubic inches per inch. So we can go cubic inches per inch. Now for the instantaneous, and they have the other one, 5 and 125, and we're going to do 5.01, and we're going to cube 5.01. 5.01 cubed is that 125 and 0.751. 125.751. And we need to find the average rate of change for this, which is the 125.751 minus 125 over 5.01 minus 5. All right, so here we go. We're going to take that number in our calculator. We're going to minus 125. And we're going to divide by 0.01. So 75.1501. 75.1501, and that's inches cubed per inch. Well, now letter B says find the instantaneous rate of change of the volume with respect to x at the moment when x is 5 inches. So letter B, we're going to take the limit as the difference approaches 0. So we have, a fairly large difference between 5 and 5.1, and then we even have a smaller difference. Well, we're going to make it even smaller. We're going to take it to the point where h is, the difference between the two is 0. So we have f of x plus h, so 5 plus h cubed, minus f of 5, which is 125, over h. And that's equal to the limit as h approaches 0 of, I need 5 plus h times 5 plus h times 5 plus h. So 25 plus 10h plus h squared. We're going to multiply that times 5 plus h. So we're going to run a 5 through this. 125 plus 50h plus 5h squared. And then run an h through it. 25h plus 10h squared plus h to the third. So this is going to be 125 plus 50h. No, plus 75h. All right, 75h. plus 15h squared plus h to the third, and that's minus 125 over h. So limit as h approaches 0 of 75h plus 15h plus h to the third over h. Now we can factor out one of the h's. So we have 75 plus, that's 15h squared plus 15h plus h squared. Oh, and we divided, the h canceled. So that's equal to 75 inches cubed per inch. Suppose that a function expresses an object's position s of t in terms of time t. The instantaneous velocity of the object at time t equal a is s prime of a is equal to the limit as h approaches 0 of s of a plus h minus s of a over h. Instantaneous velocity at time a is also called velocity at time a. A ball is thrown straight up from a rooftop 160 feet high with an initial velocity of 48 feet per second. Here's the function that represents that position. Describes the ball's height above the ground, s of t in feet, t seconds after it's thrown. The ball misses the rooftop on its way down and eventually strikes the ground. A, what is the instantaneous velocity of the ball 2 seconds after it is thrown? So we need to do the limit as h approaches 0 of f of 2 plus h. So we need negative 16 times 2 plus h squared plus 48 times 2 plus h plus 160, and we're going to minus f of 2, which is negative 16 times 4 plus 48 times 2 plus 160. And that's all over h. So we have the limit as h approaches 0 of negative 16 times 4 plus 4h plus h squared plus 96 plus 48h plus 160 and minus, let's find this value right here. So we have negative 16 times 4 plus 96 plus 160. And we get 192. 192. All right, that's limit as h approaches 0 of negative 64 minus 64h minus 16h squared plus 96 plus 48h plus 160 minus 192. Now all of those constants should cancel out. Let's see if they do. Let's drag this over here. We got negative 64 plus 96 plus 160 minus 192. And we get 0. So all of those constants cancel out. We got the limit as h approaches 0 of negative 64h minus 16h squared plus 48h. Wasn't it 60? Oh no, let's see. Oh yeah, we got this over here. We got 2 h's. And that's over h. So limit as h approaches 0 of negative 64 plus 48 is negative 16. Negative 16h minus 16h squared over h. And we can factor out an h on top. We get negative 16 minus 16h. And when we plug in 0, we get negative 16, and that's feet per second. So it's actually falling. B, what is the instantaneous velocity of the ball when it hits the ground? Well, let's find out when it actually hits the ground. So what we're going to do is we're going to graph this function, negative 16x squared plus 48x plus 160. And we can go zoom 6. And this starts with a certain height. And if we want to find the 0 when it falls, we could probably get a little better view of this. Actually, we can go 0 to, let's say, 10. And the y seems to be 0 to, I don't know, let's go 200 by 50s and maybe you get a better view of this. There we go, much better view. So we're going to calculate a 0, and it looks like 5 to me. So we're going to go 4 to 6, guess 5, and it is actually 5. So we're going to go limit as h approaches 0 of 5 plus h squared. Actually, negative 16, isn't it? Negative 16 times 5 plus h squared plus 48 times 5 plus h plus 160. And we're going to minus negative 16 times 25 plus 48 times 5 plus 160. And that's going to be all over h. And we end up just doing a lot of algebra for this. We have the limit as h approaches 0 of negative 16 times 25 plus 10h plus h squared plus, let's see, 40, carry the 4, is it 240 plus 48h plus 160 minus, let's get this number here. We got negative, let's get out of this, negative 16 times 25 plus 48 times 5 plus 160. That's not 0. Oh, is it? Oh, yeah, because the height is 0. Yeah, of course it's 0. All right. Over h, because we found out when the function is 0. All right, very good. So negative 16 times 25. Negative 16 times 25. That's going to be negative 400. So negative 400 minus 160h minus 16h squared. And then plus 240 plus 48h plus 160. Now all those constants should cancel out. Let's see if they do. We got negative 400 plus 240 plus 160. So those cancel out, and we have the limit as h approaches 0 of negative 160h minus 16h squared plus 48h over h. And we can cancel or factor an h out on the top and cancel it with the bottom. We get negative 160 minus 16h squared plus 48, and we're going to plug 0 in for h. So we have negative 160, that's actually going to be h to the first power, plus 48, so that's going to be negative 118 feet per second.